Okay, we have been talking about storage for a while, but we also have compute unit in our architecture. So let's quickly talk about how we want to analyze the compute unit. So we have the storage level, as we discussed before. We also have this compute unit. Let's imagine that we have two channels that's sending the operand A and B with their associated metadata from storage to compute. Our baseline compute unit modeling has two parts. First is an operand alignment unit, which checks whether the operand it receives are corresponding to each other. So basically, it will take in the metadata if there's any for each operand. It will check whether, according to the problem specification, it will check whether these two metadata correspond to each other. If they correspond to each other, the operand alignment unit will send a select signal to, as you can see, the two maxes next to them to choose the actual payload of whatever is sent as the operand. And if it realizes one of them does not correspond, it will choose the 0 default value. And the second part of the compute unit is the compute engine, which takes in the two operand decided by the operand alignment unit. So if we're missing one operand, what the compute unit by default will see is a 0 and a actual payload. So let's see how this baseline compute unit works with a simple example. So basically, as you can see in this figure, we also classify the computes into different types. This is slightly different from the storage unit because once we reach compute, we have to care about two operands and their data representation also matter. So as you can see in the green column, all of these is dependent on the occupancy of the fiber as well as the data representation. So you could have the most basic case, two empty elements being computed with each other. So meaning actually these two elements are both non-zero value, and of course if there are non-zero values they will be present and you are doing a computation to them, so they will definitely lead to a compute. You could also have a case where one of the operand is non-empty, the other is empty, meaning you have a zero value, a non-zero value that could lead to a compute. You could have a non-empty element and another operand being not exist. This is a case where the operand alignment unit will figure out that, okay, we're missing one operand, so what I'm going to do is I will send this non-empty operand to the compute unit. For the non-exist operand, I will use the max and send the default 0 to the compute unit. And this could also result in a compute. You could also have two empty elements. Well, both of them are 0 and sent to the compute unit to perform a computation. Again, you could have an empty element and non-exist element. And here is also a case where the operand alignment unit will send this 0 as well as a default 0 inserted by the max to the compute unit to do a computation. So all of these cases will lead to a computation. So now let's look at an example of how this compute unit works in a baseline case. Again, we're working on a dot product with A representing coordinate payload, B also representing coordinate payloads. And of course, we need to store both A and B payloads in main memory as well as the coordinates in main memory. And as you can already imagine, there is an important dimension which is k. K is a contracted dimension because in the end, after we perform the dot product, our z dimension is gone as we're accumulating on this dimension. So it is important for us to align the k value for the A operand and B operand we see. So let's see how this works. So in the first cycle, note that we didn't apply any optimization other than the coordinate payload representation of A and B. So essentially what would happen in main memory is each operand will be read out sequentially based on their representation. So in the first cycle, we're reading out the coordinates and payloads of the first A and B that is non-zero. And the first A that's non-zero is at coordinate 2, the first B that's non-zero is at coordinate 1. So what would happen is then the operand alignment unit realizes that, okay, I have a B with K equal 1, however, I don't have an A with K equal 1. So what the operand alignment unit would do is it will send B and it will send a 0 for A operand because it doesn't see an existing A that correspond to this B value. So the H will be sent, will be received by the compute unit, and the artificial 0 will be inserted, and the compute would happen. And then because we didn't use our A, we probably only need to read B out of the main memory. So then we have the next B value, which is at coordinate 2 with a payload of I. Now A and B aligned, both of them are at K equal 2, so we perform a computation of A and B, where the operand alignment unit send both payloads, C and I, and then we can proceed as normal, so we will read out the last element in both A and B data representation, and they correspond to each other, so we do a computation of D and J. So this is how the baseline compute unit will work, and as you can imagine, we are having different types of computes. There is really no space for me to show which one is which type, but I think it's pretty straightforward to figure out which compute belongs to which. So for example, the first compute is really a non-empty with a non-exist. The second compute is non-empty, non-empty. The third compute is non-empty, non-empty. Okay, again, sparse optimizations will lead to different types of compute. Essentially, it will reduce the computes that happen and turn that into a compute that really doesn't spend any energy. So let's look at this specific sparse optimization, which is gating. Gating, again, explicitly saves energy of a compute when one of the payloads of the operand element is empty. So when it sees like one of the operand is 0, it will say, okay, I saw a 0, I'm going to gate. And as you can imagine, this optimization is only associated with the compute engine because it looks at the actual value sent to the compute engine. So whenever a compute engine sees a 0, it will gate itself. So let's look at an example. Again, we have the same A and B represented in the same format. Now we have our compute being gated with the gating optimization applied. In the first cycle, again, we're reading out the first elements of A and B. A has a coordinate of 2, B has a coordinate of 1. Now the compute unit is gated because it realizes that there is no A to do the computation. And how does it realize it? The process is like this. So A, again, with a coordinate of 2 and B with a coordinate of 1 reach operand alignment unit. As you have seen in the baseline case, operand alignment unit will send a 0, an artificial 0 for A operand, and the actual payload of B to compute unit. And because we have this artificial element, due to the fact that A doesn't exist, compute will gate based on this artificial 0. So that's why we have a gating happening in the second cycle. We'll read out B, and because both of them are non-empty, gating wouldn't make any difference. We'll proceed with a normal computation for the next two computes. As you can imagine, skipping will lead to skipped computations, and only some cases allow you to skip, right? Because skip is skipping over compute, one of the payload does not exist. So this is related to the operand alignment unit. It will skip the computation if it realizes that the metadata of the two operands don't match. So this will only happen if your operand does not exist. So skipping cannot skip over empty elements. So as you can see here, we're only introducing skipped compute if one of the element is not exist. So only the third large category and the last large category would have skipped compute. Again, let's look at an example of a dot product workload with a compute unit that has skipping optimization. So in the first cycle, we are reading out the first element of A and B with not matching A and B coordinates. So we have coordinate for A being 2, coordinate for B being 1. And because of this, and one assumption that we also want to make is we have big enough bandwidth where we are also able to read out the second B as well. So then in the queue that we showed for the compute unit, there is actually 2 B values, two set of B operand data and 1 set of A operand data. And in the second cycle, the operand alignment unit will be examining what is in this queue. We'll realize that the first B coordinate does not match with A coordinates and is less than A's coordinate. So we will go ahead and look up the second B coordinate, which is BC1. And because it is able to skip ahead, then you'll, in the same cycle, realize that we do have a non-empty B value to multiply with a non-empty A value. And here is why we have this compute of C and I appearing in the second cycle. For the storage, we are just keeping reading out A and B operands. And of course, because we have the last element of both A and B vector being non-zero, we'll perform the compute D times J. So with this skipping optimization applied, as you can see, we're saving 1 cycle. Of course, this is based on the assumption that it is possible that there are two sets of B values in our queue. If there isn't 2 sets of B values, then skipping wouldn't help. So you can imagine in the analysis, the bandwidth of reading out A and B matters, and the skipping will perform worse if we do not have enough bandwidth. We have been talking about dot products for a while. I want to present another workload, which is a simple cross product, and I want to show that a actual data flow, so a mapping or a data flow, actually impact how your sparse optimization will help. So in this example, we are looking at a cross product where essentially what happens is we'll go through each element in A and B, and we multiply each A with every single one of B. So we're arriving at a output Z with dimension M and N, which is not shown here, but we're performing many more computations in this workload. And one very important difference between this workload and the dot product workload is the fact that we don't have a contracted dimension in cross product. There is no alignment needed by the operand alignment unit because you want to multiply every A with every B anyways. So there is no need for an alignment to be done. So let's see what would happen with this workload. Again, we have A and B represented in coordinate payload format, and they are stored in the main memory. Okay, so now we again read out A and B, the first element of A and B, and there is no compute, there is a bubble in the compute because of pipeline. We would do a computation of A and B. because it's a cross product, we do want to multiply C and H. So we do a computation, we read out the second element of A and B, we do a computation, we read out sequentially read out the other elements in A and B, and we perform computation. And there is no alignment needed, so we're essentially reading out things and performing computation. And as you can see in this process, there is no cycle wasted, there is no ineffectual computation happening as well. And if we apply gating and skipping, you can see that nothing actually will change because of the fact that there was already no wasted cycle or wasted computes in the original cross product. And this is mainly due to the fact that we are having a problem specification where there is no contracted dimension. So gating and skipping does not make a difference. And the high-level idea in this example is basically we need to care both about what optimizations are applied as well as what data flow you are looking at or what problem specification you are looking at. The behavior of the hardware will be different if we are looking at a totally different workload. So we have been talking about various storage and compute optimizations features. We definitely have more modeling capabilities, and these capabilities are more related to the fact that we'll usually not have a main memory with a compute architecture. It's more realistic for us to have a multi-level architecture with multiple levels of storage levels, as well as a spatial fan-out of storage levels and compute levels. And as you can imagine, we can apply these optimizations at various points in our architecture. So the first more advanced modeling capability is zero gating and zero skipping at intermediate storage level. And as you can imagine, because you're gating and skipping at an intermediate level, there is some propagation impact to the lower storage and compute levels as a result. And there is also the question of how do you want to choose this gating or skipping computations implementation? Do you want to skip A based on B or skip B based on A? And this actually matters if you have different data flow or different problem specification. We are able to internally choose the better option for you if you allow us to do so in the framework, or if you don't, then of course whatever you specify will be modeled. So this is another thing that we support. We also are able to look at more modeling with the multi-rank compression formats. As you can imagine, when you are tiling the tensor more, you're introducing more ranks, so then your compression becomes more complicated. So there is an interaction between your compression formats and the mapping. You could also be flattening some ranks. For example, usually for DNN workloads, we will be flattening the RNS dimension of the weights, or we'll be flattening the C and N for input activation. So there is a lot of ways to flatten ranks, and is especially important for workload with many more dimensions. We could also model decompression at inner storage levels. There are a lot of architectures where only the data at DRAM is compressed for saving DRAM transfers, but on-chip data is not compressed, and that also introduces some modeling complexity as well. So now we have talked about how once we have defined the statistical nature of a fiber, we could also apply sparse optimization feature and how they interact with each other. The result of this interaction is basically an analysis of the additional storage capacity required by metadata, which is dependent on your sparse optimization's data format choice, for fiber data access savings and metadata access overhead, and also your compute savings. And you can imagine, since all of our analysis are done based on fibers or a tree of fibers, we could apply appropriate scaling based on the density, based on the dense traffic to fiber shape ratio. So for example, if your dense traffic says I have transferred 5 fibers to the next level, then we could appropriately scale the per fiber savings and overhead to arrive at how much is saved and how much overhead is incurred for all of these 5 fibers. So this allows us to decouple the dense traffic analysis with the sparse optimization impact analysis in a very clean way. And this falls back to the point that we do want our analysis to be decoupled and thus have tractable complexity. And by applying this appropriate scaling, we're then able to generate the required hardware capacity at each level, as well as the resulting sparse traffic of the storage and compute units. And you can imagine these information will be used together with the hardware attributes of the architecture components and finally arrive at the amount of energy consumed and the amount of cycles spent.